What's up, everyone? We're here in 9.6, and now we're going to look at a very special application to our exponential and logarithmic functions, and this would be exponential growth and decay. All right. So let's say we're working with an exponential function, y equals a times b to the power of x. All right. Now this equation is going to represent the situation of exponential growth as long as a is greater than 1 and b is greater than 1, okay? And if you were to look at a graph of an exponential growth situation, it would look something like this, okay? As you move from left to right on the curve, as your x values are increasing, so are your y values. So that's the idea of growth, okay? And then exponential decay would occur if a is greater than 0, but b is a number between 0 and 1. Okay, that curve would be doing something like this. Right? So as your x values are increasing, your y values would be decreasing. Okay, now let's kind of illustrate this a little bit more for you. All right, so right now you can see I have a situation of exponential decay. That's because the base of this function is a number smaller than 1. But you can see the second that that base becomes larger than 1, I end up with a growth situation. Okay. All right. Now, we have two models, an exponential decay model and an exponential growth model that apply to some real world situations, okay? So the exponential decay model is the formula y equals a times 1 minus r to the power of t, and then for growth, I have y equals a times 1 plus r to the power of t. So notice the only difference between the two is whether r is being added or subtracted from 1. Okay. In both these situations, A is going to be your starting value. R is going to be your rate of growth or decay. And it'll have to be expressed as a decimal to utilize the equation. Y is going to be your ending value. And then T is, of course, going to stand for time. Okay. All right, so based off of all of this, are the following equations, are these exponential growth or decay models? All right, so y equals 3 to the power of 1/5, or y equals 3 times 1/5 to the power of x. Focus on the base here of 1/5. The fact that that's smaller than 1 tells me this is a decay situation. All right, similarly, right here, the base 1 minus 0.3, that's a number that is smaller than 1 as well. So this is also a decay situation. All right. 1 plus 0.3, that's going to be a number larger than 1. So this is a growth situation. And then for this last one, bottom left, two things to focus in on. Your A value, or I'm sorry, your B value, your base, it's larger than 1. However, notice you have a negative exponent, okay? So this is really going to be equivalent to 5 to the power of 2/5, or I'm sorry, 5 times 2/5 to the power of x. So once I see it written like that, I know that this is a decay situation, okay? All right, now let's get into some word problems where these models come into play. Let's say a cup of coffee contains 130 milligrams of caffeine. If caffeine is eliminated from the body at a rate of 11% per hour, how long will it take for 90% of this caffeine to be eliminated from the person's body. All right, so is this a decay situation or a growth situation? Well, I think a key word here is eliminate. Over time, the amount of caffeine in your body is going to decrease. So this is going to be a decay situation. And that just tells me to use the model y equals a times 1 minus r to the power of t. All right. So a few things I need to identify here. A, in this case, is 130 milligrams of caffeine. R is 11%, okay, which I need to express as a decimal, 0.11. All right. T is the unknown. Notice the question, how long will it take? So that means time's unknown. And then Y is got to be based off of the fact that I want 90% of the caffeine to be eliminated from the body. Well, if 90% is eliminated, then how much would be left in the body? It would be 10% of the original amount. So I'm going to take 10% or 0.1 of 130 milligrams, and that would be, of course, 13 milligrams. Okay. All right, so substitute everything into our model here. 13 for Y, 130 for A, 0.11 for R, and then we're solving for T here. Okay, notice I have an exponential equation where I'm trying to solve for the exponent. This is going to require the use of a logarithm. Okay, before I do that though, I need to divide both sides by that A value of 130. Okay, so that's going to be 1/10 is equal to 0.89 to the power of t. Okay, or you can say 0.1 equals 0.89 to the power of t. It doesn't really matter. All right, so at this point, I'm going to use a common logarithm. I'm going to take common log of 1/10, or how about we rewrite that as 0.1 equals the common log of 0.89 to the power of t. Now apply a power property. Bring t down in front. Divide both sides by the common log of 0.89. Okay, and we'll pull up a calculator here and see what we end up with. All right, so common log 0.1 divided by common log 0.89. Okay, I'm ending up with 19.7576 hours. So it's going to take the better part of a day for that caffeine to work through your system. All right. Okay, next example. The population of a city of 1 million is increasing at a rate of 3% per year. If the population continues to grow at this rate, in how many years will the population have doubled? All right, keyword here, grow. This is a growth situation. So we're using the model y equals a times 1 plus r to the power of t. All right. Now let's see, our starting value is 1 million. All right. Our ending value, we want to be double that, so 2 million. Our rate of growth is 3%. So that's 0.03 expressed as a decimal. And then notice again in how many years, that tells me t is the unknown. All right, so we wind up with 2 million is equal to 1 million multiplied by 1 plus 0.03 to the power of t. Now, if you divide that 1 million out, you'll end up with 2 is equal to 1.03 to the power of t. Use a common logarithm again on both sides. Apply a power property to bring t in front. And then divide out common log of 1.03. All right, and let's see what we end up with. So common log of 2 divided by common log of 1.03. So 23 and a half years, 23.4 years for this population to double.